Let us discuss one numerical example here. So, here one numerical example. So, Chennai and Mumbai are two of the cities competing in IPL. There are also many others. The organizers are narrowing the competition to the final 5 cities. There is a 20% chance that Chennai will be amongst the final 5. There is a 35% chance that the Mumbai will be amongst the final 5, and an 8% chance that both Chennai and Mumbai will be amongst the final 5. What is the probability that Chennai or Mumbai will be amongst the final 5? So, whenever we will see or, that is nothing but union. If we show and, then this is intersection. So, how we can solve this problem? So, this problem will represent by the events A, B like that. So, A is the event that Chennai will be amongst the final 5. So, let A is the event defined as Chennai will be amongst the final 5. B is the event Mumbai will be amongst the final 5. Mumbai will be amongst the final 5. So, then according to the given problem, what is the probability of A? Chennai will be there is 20% chance that Chennai will be amongst the final 5. So, 25% chance, 20% chance means 20 out of 100. So, this is 0.2, and probability of B is nothing but what is the chance for Mumbai? There is 35% chance that Mumbai will be amongst the final 5. So, this is 35 by 100. So, this is 0.35, and also it is given Mumbai will be among the 30% and an 8% chance that both Chennai and Mumbai will be amongst the final 5. So, whenever it is both, that means it is nothing but the intersection. So, Chennai and Mumbai, it will be amongst the final 5. Probability of A intersection B, it is given 8%. So, 8 by 100, this is 0.08. Now, question is given, what is the probability that Chennai or Mumbai will be what is the probability that Chennai or Mumbai will be amongst the final 5. So, basically it is or, so we will find the probability of A union B. It is asked to find the probability A union B, probability of A union B. Now, we will apply the theorem 1.7. So, this theorem we have just proved now the theorem 1.6. So, now by theorem 1.6, this is probability of A plus probability of B minus probability of A intersection B. So, just now we have proved this. So, all these values are given. This is 0.2, this is 0.2 plus 0.35, minus probability of A intersection B is 0.08. So, just we have to simplify this thing. So, 0.055 minus 0.08. So, 7 and 4, I think 0.47. So, this solution also it is you can find here. So, this is here the solution it is given. A is the event that Chennai is amongst the final 5, let B the event that Mumbai is amongst the final 5, and given probability of A is 0.2, 0.35. Already we have done all this thing. Question is that probability of what will be A union B question. So, and means intersection, or means union. So, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. 0.20 plus 0.35 minus 0.08, this is equal to 0.47. So, this is the answer the Chennai and Mumbai both will be amongst the Chennai or Mumbai will be amongst the final 5. This is OR, A union B. So, this is one numerical example related to these theorems. Now, this is the last theorem. There may be many results. So, some of the basic results that minimum that we think it may be frequently we will use in the future. Other result whenever it will be required, we will again discuss and prove it. So, here the last theorem here 1773, for any events A and B, probability of A will be probability of A intersection B plus probability of A intersection B complement for A. So, this is theorem 17. For any event, any two events A, B, this is basically C, that means it is also subset, A is a subset of B, subset of S, because it is subset of S, and B also subset of S. Probability of A can be represented as probability of A intersection B plus probability of A intersection B complement. So, if you show it by a Venn diagram, suppose this is S, this is A and this is suppose B. So, this is A and this is B. Now, A can be represented as A intersection B, this is the part of A intersection B, this is A intersection B, and plus disjoint this part is that the remaining part is this. So, what is this? This is nothing but if you take the B complement B dash. So, B dash is all this value other than the B and take the intersection with A intersection B complement is this part. So, this part is nothing but A intersection B complement. So, this is union of A intersection B complement with A intersection B. So, how we can prove analytically? Graphically we can see this. So, any event B is a subset of S, since B is a subset of S, B union B complement is nothing but S, and also B intersection B complement is nothing but null set. So, it is null set. So, B is a subset of S, that is why B union B complement is S and B intersection B complement is the null set. Now, since A is a subset of S, what will be A intersection S? It is nothing but A. So, that means A can be represented as A intersection S, which is nothing but A intersection S is nothing but B union B complement. So, now if you use a distributive property, it is nothing but A intersection B union A intersection B complement. Now, this A intersection B and A intersection B complement will be disjoint, because B intersection B complement already it is disjoint. Now, any element belongs to A intersection B means it belongs to B. So, now any element belongs to A intersection B complement, that means it belongs to B complement also. So, now this element any element cannot be in both the part, because if it is both the part, then it will be both the B and B complement. So, but B and B complement null set. So, that is why A intersection B and A intersection B complement, this will be disjoint. So, now probability of A can be represented as union of two disjoint set A union U B union A intersection B complement, A intersection A union A intersection B union A intersection B complement. So, now these are disjoint by we have in the axiom 3 also we wrote, but in axiom and theorem 1.5 we have proved it, that for finite disjoint collection of set where is mutually disjoint, this is can be we can add these two probabilities plus probability of A intersection B complement. This is by you can say axiom 3 or you can use theorem 5. Theorem 5 we have proved this result. Theorem 5 finite collection, probability of A is equal to probability of A intersection B plus probability of A intersection B complement. So, this is one of the important theorem. Later we will see that there are many applications. So, these are some extensions. So, suppose let B1, B2 Bn be a pairwise mutually disjoint, pairwise mutually exclusive, and exhaustive set of events. Suppose B1, B2, Bn be a pairwise mutually exclusive and exhaustive set of events. So, that means what we know by this definition? We have already discussed that pairwise mutually exclusive, and that means Bi intersection Bj, this is pairwise mutually exclusive for I not equal to j, I is 1 to n, j is 1 to n, and if you take the union, B1 union B2 union Bn, this will be whole S. So, it is like a partition of the set S. Then for any event A belongs to C, that means A is a subset of S, probability of A is nothing but probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection Bn. So, how we can prove that? So, just we use the previous concept, since A is a subset of S, A can be represented as A intersection S. Now, A intersection S, S can be represented as like this, B1 union B2 union Bn. By distributive property, A intersection B1 union A intersection B2 union like this union A intersection Bn. Now, what will be the probability of A? By left hand side, probability of A will be, this is nothing but probability of A1 intersection B, it is not A1, sorry, A intersection B1, A intersection B1 union A intersection B2 union A intersection Bn. Now, since B1, B2, Baj are pairwise mutually exclusive events, this A intersection B1, A intersection B2 also will be pairwise mutually exclusive events. So, that can be shown like, if you take any ij, this is intersection of A intersection Bj, this is nothing but A intersection Bi intersection Bj, which is equal to phi for I not equal to j. So, that is why they are pairwise mutually exclusive events. Now, using theorem 5, because they are pairwise mutually exclusive event, this is nothing but probability of A intersection B1 plus probability of A intersection B2 plus probability of A intersection Bn. So, this result again we will discuss whenever we will discuss the how to find the probability of a total, which it is called the total probability of event. So, that means if you have this kind of partition, so then we can write like a total probability, like graphically we can represent like it is like a S. So, then if suppose you have some kind of partition like this for any event A, that means all are pairwise disjoint, any event like actually this is part of this partition with some B1 intersection, part of this B2, part of this B3, part of this B4 like this. So, this is the representation. So, that is the some of the important theorems we complete now. Now, next we will discuss some other results. Next we will discuss new topics. So, whenever if you require some more other some of the important results, again we will prove. These are the basic things, very basic things, you may have learned it earlier also, but formally we wanted to prove it because there will not be any doubt that whether we are using just assuming it, we have already proved from the axiom. So, that is why we proved all this result. This example we have already discussed. Now, next we will discuss the conditional probability. Now, we will discuss the new concept conditional probability. Sometimes we are given some information in the form that some event is already happened. Initially, we have some associated to a random experiment. Suppose random experiment, let us consider one example, random experiment rolling a die. Then the sample space, you know that the sample space corresponding to rolling a die. So, this is this second example of sample space we discussed. S2 is 1, 2, 3, 4, 5, 6. Now, suppose in the other room someone rolling the die and then there is no any other information, then probability of suppose this event, suppose 2, this is the event, suppose one event let us consider whenever we are rolling a die, let us consider one event A is 2 is observed on the top face. Now, suppose someone gave the information in the form that 2, 4, 6 instead of, so whenever there is no information, so any of the observation it can come with the assumption that all the faces are equally likely by symmetry, the probability will be 1 by 6, any of the observation it will come. So, probability of A will be 1 by 6, 1 out of 6 by classical approach, definition of classical approach by the assumption that all the observation are equally likely. Now, suppose this information is given provided to us that someone saying that the die is rolled and someone have already observed that this is a even number. So, even number if we have this information, then with this information we can understand that now probability of any odd number, what is the probability that the odd number now it can come, because we already know that it is even number. So, odd number there is no possibility now. So, probability of any of the 1 or 3 or 5, this will be 0, and probability of any of the even number, now what is the probability that this 2 will appear. So, in that case we denote this kind of notation, we say this probability, now probability of A is 1 by 6, but probability of A we say this notation A given B, that means the information B is given to us. So, this is called the conditioned, that conditional probability. This is the different than this. So, now from the intuition we will discuss the proper definition of conditional probability. Before that, from the intuition we understand that probability of any of the odd number will be 0. Now, if this is a even number occurring. So, one of the even number, what is the probability that 2 it may come, because now the sample space changed. Earlier the sample space was 1, 2, 3, 4, 5 and 6. Now, the sample says whenever somebody says that even number occur, now we are considering this should be the possible sample space. Now, given this information, our sample space is nothing but 2, 4 and 6, and out of these 3 observation, only 3 sample space contain only 3 equally likely points, and what is the probability that 2 may appear? This is 1 out of 3. This is from the intuition. So, another example, it is called, so this is written here. Suppose before observing the outcome of a random experiment, you are given information regarding the outcome. How should this information be used in prediction of the outcome? Namely, how should probabilities be adjusted to take into account this information? Usually, the information is given in the following form. You are told that the outcome belongs to a given event. You are told that an event has occurred, like here even number occur. So, one of the interesting example here, it is called prisoner dilemma. So, prisoner dilemma, there are 3 prisoners A, B, C in a jail. So, one of them will be executed and other 2 will be set free. So, in that situations, so there are 3 prisoners A, B and C. So, this is the sample space, 3 prisoners in a jail. Now, one of them will be executed. Suppose A denote the event that A will be executed, B denote the event that B will be executed and C denote the event that C will be executed. And by equally likely, probability of A will be 1 out of 3, probability that A will be executed 1 by 3, that is same as probability B will be executed 1 by 3, probability C will be executed 1 by 3. So, probability of A complement, if we by definition this is 1 minus this property we have studied, this is 1 minus 1 by 3, this is 2 by 3. Similarly, probability of, so sometimes we are writing by bar. So, whenever, so we can different book, different references you see that, so there are different notation we are following also. Probability A complement or A C or A bar, it is probability of A bar is 1 minus P, this is 1 minus 1 by 3, 2 by 3. Probability of B complement is B bar, probability of B bar is 1 minus probability of B, this is 1 minus 1 by 3, again this is 1 by 2 by 3. Similarly, probability of C bar, it is nothing but again 2 by 3, 1 minus 1 by 3. So, those information it is we are getting whenever we do not have any other information, it is given that there will be in a jail 3 prisoners, 1 will be executed and 2 will be set free. Now, the prisoner A, he thought somehow he can get some additional information. So, he could ask the question that please tell that whether I will be executed or not directly. So, the guard may not provide the information. So, instead of asking this question directly, A thought that he will ask in a different way. So, he is asking because do not give any information about me, but among B and C, because one will be executed we know, among B and C one will be set free. Please give this information who will be set free among B and C. So, A wants this information in term of please tell me that whether B complement may happen or C complement may happen. So, that means one of the event will happen. So, it is uncertain. So, that is the question A asked. Now, guard thought that how this information may be utilized. In this information how A can be get benefited. So, guard thought that if I say let the information is given B complement is happened or observed. So, B complement means B will not be, so that means B will not be executed, B will not be executed. So, that is going to be happen. So, that means B bar is given. So, we can say that guard give the answer that B bar is happened or B will not be executed. So, given now given this information, given B bar, now what is the probability of A now? So, given A bar, B bar, we want to find the, now what is the chance of execution of probability A, sorry probability of A. Given B bar, we want to find probability of A. We want to find the, given B bar, we want to find the that means here we are talking about, we give this notation, we want to find probability of A given B complement. So, B complement is given, that means B will not be executed. Then what is the possibility? Either A or C can be executed. Now, from the intuition, now what will be the probability? Initially probability of A is 1 by 3. Now, probability of A given B complement, this probability from the intuition, because B complement happened already, that means we know that B will not be executed. So, then among the A and C, now the sample space become, so this sample space given this information, now the sample space change to only A and C. So, out of A and C, what is the probability that A will be executed? Now, because there are two elements by equally likely, probability of A equal to probability of C, they are equally likely, out of 2, 1 will be executed 1 by 2. So, that is from the intuition we can get this probability, but we have to formally define it, what is the probability. So, how to find the probability, conditional probability, because from the intuition we may not able to compute or it is not formally defined, we have to define formally. So, that we will define, but before that there is very simple examples, so that we can understand that how a given information can be utilized to find the probability of a event. Now, this conditional probability, what we got the information that earlier the probability that A will be executive was 1 by 3, now probability of A will be executive given B bar, it is 1 by 2. So, that means the probability that A will be executive is increased. So, guard says that whether you want to increase the probability of your death. So, that is the, here it is written that 3 prisoners A, B, C are in jail, one of them is to be executed and the other 2 will be set free. Prisoner A asks the guard, one of my partners B or C will be set free. Could you please tell me which one of them will be set free? Guard thought a while and told A, if I do not tell you, then your chance of death is 1 by 3, but if I tell you, then there are only 2 left and you are one of them to be killed. Your chance of death will be 1 by 2. Do you really want to increase your chance of your death, increase your chance of death? So, this conditional probability, it is utilized to find the probability more appropriately.